Welcome back to the course of Applied Elasticity. In the previous lecture we were talking about the stress measures, and in this lecture as well we will continue with the topic of stress measures. Earlier we were talking about the Cauchy stress tensor, which was a stress measure in the deformed coordinate system. Now in today's lecture we are going to talk about the stress measures with respect to undeformed coordinate system. So, to have a quick recap, if we are considering a small infinitesimal volume or cube element centered at point P and sides aligned along x1, x2, x3, three orthogonal axes, the Cauchy stress tensors were defined as the true stress components, which are nothing but the measure of the current force acting on the current configuration per unit current or deformed area. So, here note these 2 points. The force which we are considering is the current force acting on the current configuration and defined per unit current area. So, we are considering the force acting on the deformed configuration per deformed surface area, and that is defined as the Cauchy stress. This measure is also called true stress because we are considering the deformed surface area, not the original or undeformed surface area. So, in the undergraduate solid mechanics you must have heard about the difference between the engineering stress and the true stress. Engineering stress takes care of the undeformed surface area, whereas true stress takes care of the deformed surface area, as the Cauchy stress is defined as the current force per unit deformed surface area. This is a measure of true stress. We had shown that T equals to sigma transpose n, relation between Cauchy stress tensor with the surface traction vector T, which in the initial notation can be written as T I equals to sigma j I n j. We had also shown that the Cauchy stress tensor is symmetric, thus sigma I j is equals to sigma j I. Now, moving forward to the definition of Payola-Kirchhoff stress tensor. So, we are having two different Payola-Kirchhoff stress measures. One is called first Payola-Kirchhoff stress tensor, second one is called second Payola-Kirchhoff stress tensor. These are the two stress measures which helps us to measure the stresses in the undeformed configuration with respect to undeformed area. These are equivalent to the engineering stress measures. So, how are they defined? First Payola-Kirchhoff stress is defined as the force acting in the current configuration per unit surface area of the undeformed configuration. So, here force is taken from the current configuration, force acting in the current configuration divided by the area in the undeformed configuration. So, though we are taking the force from the deformed configuration, but area is taken from the undeformed configuration. This is the definition of first Payola-Kirchhoff stress tensor. Whereas, for the second Payola-Kirchhoff stress tensor, the definition is like this is the transformed current force acting per unit undeformed or initial surface area. So, here instead of current force we are taking transformed current force. So, some kind of transformation is required by which we are taking the current force back or map to the initial configuration. So, we are doing some force transformation here, and that divided by the unit undeformed surface area. This defines the second Payola-Kirchhoff stress. So, we will look into the mathematical description for both of these two stresses. So, starting with the first Payola-Kirchhoff stress tensor. So, this P tensor is used. You can see this capital P, this is used to denote the first Payola-Kirchhoff stress tensor. Sigma is used to denote the Cauchy stress tensor, P is used to denote first Payola-Kirchhoff stress tensor, and capital S is used to denote the second Payola-Kirchhoff stress tensor. Now, let us consider this initial configuration of the body defined by capital omega naught at initial time t naught. We are considering a small area element d capital A with unit normal capital N vector on the surface of this particular undeformed configuration body. Now, T vector, capital T vector being the traction vector acting on the small area d capital A. The total vector traction we can write as capital T times dA. This is the force acting on this small area dA, d capital A in the undeformed configuration, and this can be written as P times N dA. How is it coming? That we will discuss afterwards. So, the force acting on the small area dA is capital T times d capital A, where capital T is the traction vector acting in the initial configuration. Now, moving forward, if you are going for the transformation which is defined through deformation gradient tensor F, in the current configuration body is shown here with capital omega at any time t. The area d capital A is now deformed to d small a with unit normal small n vector, and small t vector being the surface traction acting in the deformed configuration. So, the force acting on the d small a, the deformed surface area, is small t, the deformed surface traction, times d small a, the deformed surface area, and using the relation between the surface traction small t in the deformed coordinate and deformed coordinate stress measure, that is Cauchy stress measure, which is T equals to sigma transpose n. This quantity is equals to T, sigma transpose n is equals to T, that we had proved. So, force acting on the current configuration on the deformed area d small a is equals to T times dA, small t times d small a, and that is sigma transpose n times d small a. So, force vector acting on the deformed area element in the deformed configuration is denoted by d small f, which is shown here in the figure, and that is equals to T small t times d small a equals to sigma transpose n d small a, and using the symmetry of the Cauchy stress tensor, d small f vector is equals to sigma n d small a. Now, moving forward, d small f equals to sigma transpose n d small a, which we had just proved. Now, we are coming to the formal definition of first Payola-Kirchhoff stress tensor, which is defined as d small f is equals to P acting over capital N times d capital A. So, this relates the current configuration force d small f. D small f is the force in the current configuration, and d capital A is the area in the undeformed state, the initial configuration. So, area in the undeformed state and force in the current configuration, d small f vector and d capital A, these two are related with the help of a stress measure that is known as capital P, or first Payola-Kirchhoff stress tensor, and through this particular transformation law P is defined. D small f is equals to P acting over capital N d capital A. Now, using both of this equation, this 1 and 2, as left hand side of both the equations are same, d small f, we can equate the right hand side and write sigma transpose small n d small a equals to P capital N d capital A, and using the symmetry, removing the transpose of sigma, sigma d small a equals to P d capital A, where d small a is the deformed area vector, d capital A is the undeformed area vector. Now, deformed area vector d small a and undeformed area vector d capital A can be related by the change of surface, or the commonly known Nansen's formula, which we had discussed in the previous lectures, one of the previous lectures. So, d small a can be transformed or related to d capital A with the help of this Nansen's formula as d small a vector is equals to j times f inverse transpose d capital A. Substituting that here in the left hand side, we are getting this equation J sigma F inverse transpose D capital A equals to P times D capital A. So, thus the first Payola-Kirchhoff stress tensor P is J times sigma F inverse transpose. This is the relation between P and sigma. They are related through J, that is Jacobian, and F inverse transpose, that is transpose of inverse of deformation gradient tensor. In the initial notation, we can write the components of P as P I j equals to J times sigma I k F inverse transpose k j. Now, removing the transpose sign from the last term and flipping the indices, this would be J times sigma I k F inverse j k. I have removed the transpose sign and flipped these two indices j and k. These two are flipped. Now, taking this F inverse j k from right hand side to left hand side as F j k, we are having P I j F j k equals to J times capital J times sigma I k, or sigma I k can be written as 1 by capital J P I j F j k. So, P I j F j k is basically P times F I j component, and thus the Cauchy stress tensor sigma becomes 1 by capital J P times F. So, Cauchy stress tensor sigma and the first Payola-Kirchhoff stress tensor P are related through this form, either using this or using this. If any one is known and we know the mapping deformation gradient tensor, then we can find out the another stress measure. Now, in general, F is not symmetric. The deformation gradient tensor is not symmetric in general, and thus P, the first Payola-Kirchhoff stress tensor, this stress measure is also not symmetric in general. So, that is one of the problem of this first Payola-Kirchhoff stress tensor. We are normally having the stress tensors to be symmetric, the cross shears are equal, but here even though sigma is symmetric, but F being not being symmetric, P in general is not symmetric. So, this first Payola-Kirchhoff stress tensor or P gives the current force acting in the deformed configuration per unit undeformed area. Now, inverse of this first Payola-Kirchhoff stress tensor is defined as a nominal stress tensor, another stress measure, but this is not much used in practice. So, N nominal stress tensor is defined as transpose of the P first Payola-Kirchhoff stress tensor. Now, we are moving to the definition of second Payola-Kirchhoff stress tensor, which is denoted by capital S. So, we are considering the same figure here in the initial and current configurations, where the definition of second Payola-Kirchhoff stress tensor is given as the identity D capital F star equals to S acting over D capital A. So, through this particular expression, the S second Payola-Kirchhoff stress tensor is defined. What is D F star? D capital F star is the force acting in the initial or undeformed configuration on the undeformed area that corresponds to the force D small f, which is acting on the deformed configuration on deformed area. So, as we had discussed while deriving the first Payola-Kirchhoff stress tensor, D small f is the force acting on the current configuration on deformed area D small a. Now, we are defining a force D capital F star through a mapping which maps this D small f force into D capital F star. So, similar to the deformation mapping of x we have seen through the deformation gradient tensor F, we are mapping D capital X to D small x. Using a similar mapping as D small x equals to F acting over D capital X, we are trying to define a force mapping using the same deformation gradient tensor. So, D small f, the actual deformed configuration force acting on the deformed area D small a equals to deformation gradient tensor capital F acting over D capital F star, where D capital F star is the transformed force acting on per unit undeformed area, and from this D capital F star can be obtained as F inverse d small f, and now d small f is nothing but p times d capital A vector. D capital A vector is undeformed area vector. So, putting d small f as p times d capital A and comparing it with the definition, d f star was defined as SDA. So, if you compare this with SDA, we simply get S, the second Euler-Kirchhoff stress tensor, as F inverse P, and as we know, P was already shown to be J times sigma F inverse transpose. Substituting that here, S equals to F inverse P becomes J F inverse sigma F inverse transpose. And in the initial notation, in terms of components, the components of second Euler-Kirchhoff stress tensor Sij can be written as J times F I k inverse sigma k L F J L inverse. So, second Euler-Kirchhoff stress gives the transformed current force defined per unit undeformed area, and this transformation mapping of the force from the current configuration to undeformed configuration is done with the help of deformation gradient tensor F, which is used to transform the small elemental length d capital X to d small x. Now, with this definition of second Euler-Kirchhoff stress tensor, we are now going to check whether it is symmetric or not. We had already checked that the first Euler-Kirchhoff stress tensor P was not symmetric, and P and S are related through this relation P equals to F times S. Now, let us check whether S is symmetric or not. So, the relation between S, P and sigma, that is given as S equals to F inverse P equals to J times F inverse sigma F inverse transpose. Now, taking the transpose of S, taking transpose of both the sides of this equation, S transpose would be J, which is a constant. Transpose cannot act over a constant. So, J times transpose of this entire quantity F inverse sigma F inverse transpose. Now, we had discussed that the transpose of T S by the transpose rule, this is S transpose T transpose. So, using the same here. So, considering F inverse to be one tensor, sigma times F inverse transpose to be another tensor, S transpose can be written as J times transpose of the second term first, that is transpose of sigma F inverse transpose, and then transpose of the first term, that is transpose of F inverse. Now, using the same formula once again for simplifying this first term, this would be J times F inverse sigma F inverse transpose, and I have already used the symmetry of Cauchy stress tensor sigma transpose equals to sigma here, and thus you can see this S transpose is coming out to be S. So, the second Euler-Kirchhoff stress tensor S is a symmetric tensor, and thus this is preferred over the first Euler-Kirchhoff stress tensor for measuring the stress in the undeformed or material configuration, in the initial configuration, because of its symmetry. Now, we are going to solve one example problem. So, let us consider this given deformation mapping. Small x1 is equals to capital A capital X1, small x2 is minus B capital X3, small x3 equals to capital C capital X2, where A, B, C are some arbitrary constants which are known. If the Cauchy stress tensor of the body is given as this, all terms are 0 apart from the 3 term. So, body is in uniaxial tension along the 3 axis, along the x3 axis, then only the Cauchy stress tensor can look like this, only sigma 3 term is non-zero. You are asked to find out the first and second Euler-Kirchhoff stress tensor. So, we need to find out P, which is the first Euler-Kirchhoff stress tensor, and S, which is the second Euler-Kirchhoff stress tensor. Now, for the given deformation mapping, we can easily find out the deformation gradient tensor by its definition. So, how is F defined? Fij, component of the deformation gradient tensor, is del small xi del capital Xj. So, small x1 being A times capital X1, the first row of f would be just a 0 0. Similarly, using x2 and x3 expressions, we can obtain the complete deformation gradient tensor as a 0 0, 0 0 minus b and 0 c 0. Now, J, which is required to be used for relating sigma p and s. So, J is the determinant of f or Jacobian, that is nothing but a, b, c for this present deformation gradient tensor f, and using J we can find out the f inverse. If you take the inverse of this deformation gradient tensor, f inverse would be 1 by a 0 0, 0 0 1 by c, 0 minus 1 by b and 0. So, with this matrix manipulation, now we are proceeding for finding p and s, first and second Parallel-Kirchhoff stress tensors. So, I have simply copied all the expressions which we had derived. Sigma is given, f, f inverse and j we had obtained. Now, the definition of first Parallel-Kirchhoff stress tensor P is given through this transformation. P equals to Jacobian J times sigma f inverse transpose. We already know sigma, we already know f inverse. So, f inverse transpose can be written like this. So, J is ABC, sigma is this where only one non-zero term is there at 3 3 location, and this quantity is f inverse transpose. So, I had flipped the 1 by C and minus 1 by B, these two particular entries in the f inverse transpose. Now, if you multiply the two matrices, this would be resulting 0 0 0 0 0 0 0 sigma naught by C and 0, and taking sigma naught by C out, the P first Parallel-Kirchhoff stress tensor becomes a b sigma naught times all zeros in first and second row, and third row is 0 1 0. So, this is the first Parallel-Kirchhoff stress tensor corresponding to the given Cauchy stress tensor. Now, moving forward to the calculation of second Parallel-Kirchhoff stress tensor. So, here the obtained P is also added, which we had just now obtained, along with the other quantities sigma, f, f inverse and j. Now, second Parallel-Kirchhoff stress tensor S is defined through this transformation. This is equals to J times f inverse sigma f inverse transpose. This is the relation between second Parallel-Kirchhoff stress tensor S and Cauchy stress tensor sigma. Now, instead of this, it is convenient to relate S with P, then the expression is slightly shorter. We would be needing to multiply only two matrices if you are writing S as f inverse P. You can also obtain S using this particular rule, but here three big matrices you need to multiply. So, that is why it is convenient to use the relation between S with P, the first and second Parallel-Kirchhoff stress tensor, as S equals to f inverse P. So, f inverse is already known, P we had already calculated. So, writing those two here, f inverse times P would be a b sigma naught multiplied with 1 by a 0 0 0 0 1 by C 0 minus 1 by B 0, and the P is all zeros except the location of 3 2, which is equals to unity. Now, multiplying these two, we are getting the second Parallel-Kirchhoff stress tensor S to be a b sigma naught by C times 0 0 0 0 1 0 0 0 0. So, this completes the present problem. This is the second Parallel-Kirchhoff stress tensor corresponding to the given Cauchy stress tensor sigma. For any problem, if any one of these three stress tensors sigma, P and S are given, and you know the deformation mapping, that is the deformation gradient tensor F, then it is possible to convert one the given stress tensor into the remaining two, any two other stress tensors. So, in total in this particular lecture, first we had introduced the concept of the stress measure in the undeformed or the initial configuration involving both first and second Parallel-Kirchhoff stress tensor, and then solved few example problems. Thank you.